The Large Hadron Collider is the world's largest and most powerful particle collider and the largest machine in the world. It was built by the European Organization for Nuclear Research between 1998 and 2008 in collaboration with over 10,000 scientists and hundreds of universities and laboratories, as well as more than 100 countries. It lies in a tunnel 27 kilometers in circumference and as deep as 175 meters beneath the Franco-Switzerland border near Geneva. First collisions were achieved in 2010 at an energy of 3.5 teraelectronvolts per beam, about 4 times the previous world record. After upgrades it reached 6.5 TeV per beam. At the end of 2018, it entered a 2-year shutdown period for further upgrades. The collider has 4 crossing points, around which are positioned 7 detectors, each designed for certain kinds of research. The LHC primarily collides proton beams, but it can also use beams of heavy ions. Lead-to-lead collisions and proton-lead collisions are typically done for 1 month per year. The aim of the LHC's detectors is to allow physicists to test the predictions of different theories of particle physics, including measuring the properties of the Higgs boson and searching for the large family of new particles predicted by supersymmetric theories, as well as other unsolved questions of physics. The term hadron refers to composite particles composed of quarks held together by the strong force. The best-known hadrons are the baryons such as protons and neutrons. Hadrons also include mesons such as the pion and kaon, which were discovered during cosmic ray experiments in the late 1940s and early 1950s. A collider is a type of a particle accelerator with 2 directed beams of particles. In particle physics, colliders are used as a research tool. They accelerate particles to very high kinetic energies and let them impact other particles. Analysis of the byproducts of these collisions gives scientists good evidence of the structure of the subatomic world and the laws of nature governing it. Many of these byproducts are produced only by high-energy collisions, and they decay after very short periods of time. Thus many of them are hard or nearly impossible to study in other ways. Physicists hope that the Large Hadron Collider will help answer some of the fundamental open questions in physics, concerning the basic laws governing the interactions and forces among the elementary objects, the deep structure of space and time, and in particular the interrelation between quantum mechanics and general relativity. Data are also needed from high-energy particle experiments to suggest which versions of current scientific models are more likely to be correct. In particular to choose between the Standard Model and Higgsless model and to validate their predictions and allow further theoretical development. Many theorists expect new physics beyond the Standard Model to emerge at the TeV energy level, as the Standard Model appears to be unsatisfactory. Issues explored by LHC collisions include, is the mass of elementary particles being generated by the Higgs mechanism via electroweak symmetry breaking? It was expected that the collider experiments will either demonstrate or rule out the existence of the elusive Higgs boson, thereby allowing physicists to consider whether the Standard Model or its Higgsless alternatives are more likely to be correct. Is supersymmetry, an extension of the Standard Model and Poincare-registered trademark symmetry, realized in nature, implying that all known particles have supersymmetric partners? Are there extra dimensions, as predicted by various models based on string theory, and can we detect them? What is the nature of the dark matter that appears to account for 27% of the mass energy of the universe? Other open questions that may be explored using high-energy particle collisions. It is already known that electromagnetism and the weak nuclear force are different manifestations of a single force called the electroweak force. The LHC may clarify whether the electroweak force and the strong nuclear force are similarly just different manifestations of one universal unified force, as predicted by various grand unification theories. Why is the fourth fundamental force so many orders of magnitude weaker than the other 3 fundamental forces? See also hierarchy problem. Are there additional sources of quark flavor mixing, beyond those already present within the Standard Model? Why are there apparent violations of the symmetry between matter and antimatter? See also CP violation. What are the nature and properties of quark-gluon plasma, thought to have existed in the early universe and in certain compact and strange astronomical objects today. This will be investigated by heavy ion collisions, mainly in ALICE, but also in CMS, ATLAS, and LHCb. First observed in 2010, findings published in 2012 confirmed